How's everyone doing today? Okay. So I've got this in student view so you can see everything. The focus we're on is the second exam content. We'll just pull up the schedule here. So here we are, 321, looking over the practice exam. I'll show you all the resources that are already there, the solution videos I've done previously. A few of you have seen those. And then we have, I think, about the last 5, and we'll work through those together as a solution, and I'll record them so that we can take a look at those. Yeah. Okay. So, and again, you can continue working on any of the assigned homeworks, and this will basically focus on chapters 4, 5, and 6. But remember, the largest part of the grade comes from the exam, so it's really best at this time to focus on that exam review. So then by Thursday, you'll be very familiar with what's going to show up on the exam. So I have here in the exam review, this is from fall semester, but it's the same thing they have for the new review. They did add some of those, what do they call them, skill-based practice problems. I'm not having those on the test, so I'm not going to have you go through and do those review problems. It's one of those things, if the course is generally either going to be a skills-based course or a concept-based course, which this one's more concept-based, to help you with the calculus. It's still valuable to pick up those skills, but if it's not integrated in the course, which it's not, it's really just an add-on this semester, I don't see it working well for all yours to do an extra 40 problems that are kind of separate. So that's what I'm doing. I won't have any of the skills-based, but I will have all the conceptual-based that we've been doing, because that's really what's going to help you the most. Skills do help you as you get into calculus, so review those as you want, but also you won't have the stress of having it tested on you. Okay, so there is this PDF at the top, which I'm going to download. Actually, I think I've already got it, but we'll work through it. There's also this answer key, which provides the answers, but also, and sometimes it does provide a bit of explanation of why this is right and this is wrong and such. So it's good to review them. And then below there, what I've done is I've worked each of the questions up through, I had through 19 from last semester. And last semester I had 6 classes, so it was hard to keep up with everything. I've added 20 through, I think it's 35? Yeah. So I reworked those, and I try to make them sort of as brief but as beneficial as possible. So they're somewhere between, some are as low as 2.5 minutes, some are as much as 10. But I work through and I try to not necessarily teach the concept, but explain it in a way that you could kind of understand. Okay, so these are all here. So what we'll do is there's 36 through 40 that I didn't have a chance to get done yet, so we'll do those this morning. And then if you have additional questions, we can add those in. But just know that if you haven't viewed the video and you had a question on a particular problem, I'm going to ask you to kind of take a look at that video first. It may answer all your questions. That's the goal. But between these 40 questions, does anyone remember how many are going to be on the test? 20. Excellent. So half of what's on the practice test are on there. The test is completely multiple choice. So we also give you all the answers. It's just we mix the right answers in with 4 wrong answers, right? So we're not that nice. But all the answers are there. So in a way you can use other methods that, on the review, you have to kind of walk through and go through, and that's what all this is about. But when you come to the test, if you can narrow it down to 2, and then have a good intuition about one, there's a high possibility of doing much better even on ones that maybe you're not real familiar with or real comfortable with. We want you to get as comfortable on them all as you can be, but that's the reality of it. Okay. Okay. Any questions so far, or comments or concerns? Okay, good. So I guess we went through a lot this week, didn't we? I don't know if you heard about it. I heard from the students there was I guess a online bomb threat. Turned out to be a hoax, but you know, hey, I'd take everything serious. And another student had their room got flooded, or their house got flooded. A lot of rain. There's weird things going on, but we'll keep making progress. It's a strange world. Okay, so this is the answer key, just to let you know that there are some deep explanations within here. So you can, you know, if like on number 2, you know, if you had a question about F, it does explain it. So I don't look at these necessarily. I look at them maybe after I've done what I'm doing, just to make sure that I'm on the right track as they are. But other than that, I explained it in the way I understand it. So it may be different, and hopefully is, so that we have multiple ways of getting things. So if my video doesn't make sense, maybe this will. If this doesn't make sense, maybe the video will, is kind of what I'm hoping for. So let's go to downloads. Open this up, and then I'll get my, oops. See, are we recording? And just in case we need it, I'll open up a calculator. Let's see. Maybe. Oh. Okay. Good. We are recording. Okay, good. So, and again, the exam questions are similarly worded to these. Everything that's in here potentially is on the exam. Everything in the exam is covered in these 40 questions. So there's not something on the exam that's not in here. And I'll just highlight, this is a very good question to go over, okay? So just make sure you review it. What I do in the video is I talk about each shape and what their graph would look like, which is more important than just trying to pick the right one, because the right one here, I'll tell you, in the test they give you similar shapes, but they give you a different graph, right? So you want to know what's causing that graph to look that way. And we get to the answer, but we discuss, you know, when it's like this, it's going to be a straight line here, and various things. So watch that video, and it should give you a fairly deeper understanding of what's going on. Plus, that's a good concept to take with you. Okay, so let's see. This is about where I stopped. So we got about 5 questions. We'll go through them together so that we have it recorded. I'll post it in that same place for questions 36 through 40, so then everybody has access to it. And again, what I would do is just at this point, don't worry about homework points or anything. Just worry about working as much as you can through the practice, the review test. Even if that's just sitting down, getting a bowl of Cheerios or whatever your favorite cereal is, and watching the videos. Kind of, it's a passive way of learning, but you can pick up a lot. And then maybe go back and try it on your own, you know. Okay. So let's see what's going on here. So point A, let's see. Point A is launched horizontally away from a wall. horizontally, so that's going to be this way, I guess. And A of t represent points A's distance from the wall in meters in terms of the number of seconds t since the point was launched. Point D is launched from a platform that places it 1 meter from the wall. Okay, so we know this is 1 meter. And travels 1.5 times as fast as point A. So we've got these two points traveling. Again, T would be, or D would be going this way, but it sort of has a head start, right? And it's going faster. If D of t represents point D's distance from the wall in meters in terms of the number of seconds t since the points were launched, and I guess they're launched at the same time, write a function formula for D that uses the function A of t. Okay, so what they're asking us is using function notation. So this is the hardest part, is kind of what in the heck are they even asking, right? They don't, you know, they're not asking for the function itself. Okay, that's the important part. They're not asking for 2x plus 4 or something, you know, that kind of equation. What they're saying is define D of t to be something in terms of this function A of t. So if they're launched at the same time, let's just talk about how fast they're moving. Which one's moving faster? D. How much faster? 1.5. So whatever A is doing, if we multiply, sort of this is kind of how much distance is covered, right? By time, distance per time, which is speed, right? So if we multiply this by 1.5, shouldn't that just give us D's distance? Okay, or yeah, D's speed and D's distance along. So it's kind of, this is going to go 1.5 times further in the same amount of time as A goes. Does that make sense? Okay. And is that it? No, there's one more part to this. And what's the other part? What's that? The 1 meter head start. So that would be if they both launched from the same point and going forward, we're done. But they weren't. D got a head start, so we have to say, oh yeah, D is 1 meter ahead from the very beginning, and then it's obviously going to be more ahead. But there's our function. That's it. Okay. But a lot of you, me included, when we see this, we're thinking in terms of getting an equation with something in terms of x or t or something, a linear equation, exponential, something. That's what we're taught to think. What these questions are about, and there's a number of these that are just wanting sort of function notation. What's the relationship between the functions? Which is what we do a lot in calculus. We do a lot more of that in calculus than we do in algebra. Okay? So far, are we okay? And again, some of you have been here, we've worked through these, and I've struggled a little bit because I wasn't quite sure what they're asking until I look at it. Okay, so then the graph of the function A is shown at the right. Use this information to sketch the function D. So if this is A, how is D different? Well, it certainly starts 1 higher. So instead of starting at 0, it would, I don't like the scale. So this first line is actually 2. So we have this. And then, again, you're not going to be asked to draw a graph, but if this question were on the test, you would maybe have to choose between the graphs. So what would be the relationship of the line? Would it be the same? Would it be parallel to A? No. Would it be less than A? No. It's greater. It's 1.5 times, right? So not quite twice as fast, but 1.5. And I'll just estimate it. You know, it's going to be a little bit. You could kind of maybe come out here and figure a point if you want to be real accurate. But I just know, okay, I'm looking for something like this. So if I see a parallel line, that's not going to be the right choice. It needs to be a little bit. If it's too steep, you know, that's kind of what I'm trying to do, is which one has basically a slope of 1.5 more than this slope. Okay, it's not necessarily a slope of 1.5, but 1.5 times the slope of A of t. Okay, does that make sense? Okay, that's 36. So something like so. Again, there's some that you're going to basically be interpreting graphs, some where you're just working with function notation. Okay, so clear that one out. It's 36. We'll go to 37. And let's see how far. Okay. Oh, we got ABC. We might not do all of these, but we'll see. We'll do one or six. Consider the data shown for each of the functions below. Use this data to classify each function's properties, including whether it's increasing or decreasing in the given domain. Okay, so basically, we got some data. Maybe we'll go through each of these. We're asked some information about this. So instead of being given a graph, we're given a table of values. So what we're doing, what we might be able to do is, if you wanted to, you could construct a graph out of this if you're more visually oriented. Okay, so let's take a look at A, right? And I'm just going to, oops, let's come back here. So -2, -1, 0, -8, -6, -2. So it's getting points maybe like this. There's 4, there's 12. So I've just kind of quickly sketched so I get a visual what's going on. So given the domain, the function f of x is increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, decreasing at a decreasing rate. Okay, so I guess these are true or false questions, right? So which one of these is true? Well, is it increasing or decreasing? It's increase. So, and the way that is x gets bigger, y is getting bigger. Okay. Let's look at the difference between. So how is it increasing? I go from -8 to -6 is a jump of 2. -6 to -2 is a jump of 4. -2 to 4 is a jump of 6. And then 4 to 12 is a jump of 8. Is that right? And that's for equal x increases. So that's one of the things. So as x is sort of say, y keeps jumping by bigger bounds, right? So we can say it's increasing, and is the increase getting bigger or smaller? Are the increases getting bigger? Yes, they are. Okay, so that's increasing at an increasing rate. Okay, that's what that means. That's the one that's true. These are all false. So it is increasing, but not at a decreasing. We'll see that one. Okay, so each of these we're going to look at that. So this other function, notice we go from 0 to 4, so x is increasing. We kind of look at since they're focusing on the rate of increase, we went from 16 to 8, so that was a decrease of 8. We went from 8 to 2, a decrease of 4. We went from 2 to -2, a decrease of 4 again. Oh wait, that's not 4. 8 minus 2, that should be 6, right? Okay, so be careful when you go through just. And then 4, and then from -2 to -4 is a drop of 2. So first of all, is this increasing or decreasing? It's decreasing, so it's getting smaller. So we kind of said, okay, it's not increasing. We get rid of those. And what about the rate? Is the rate increasing or is the rate decreasing? We dropped by -8. We dropped by -6. So the drops are actually becoming less and less of a drop. Less negative. This is where it gets a little confusing. When we talk about rate, it's less negative, right? The amounts are actually going down. But it's getting to be, if we were to graph this, it would be decreasing, but the decrease is slowing. So I would call this decreasing at a decreasing rate. Does that make sense? Okay, that's one I'm going to check, because sometimes, because it's less negative, they might say that that's the rate itself is actually increasing. Because if we were to calculate this rate, it would be, well, the rate between these two is -8. The rate between these two, -2, right, per one. So it's less negative, so in some cases they call that that the rate itself is actually increasing. It's going more towards positive. But the steepness definitely is going down. So I'm going to, let's just see how they define this. This is 37. See, this when I'm at home, I can look this up and then figure it out first. But I like to go through and just you know, if I make mistakes, I make mistakes, right? But we learn. Yeah, decreasing at an increasing rate. So I know that that's the difficulty, is because the rate is getting more positive, right? So as I think through this, while the steepness is decreasing, the rate is becoming closer to 0, if you will, or more positive. So they call that decreasing at an increasing rate. But this is the one that's always thrown me. It's the steepness of the increases or the decreases going down. Okay, questions on that one? Okay. So clear this out. And we kind of see what's going on here. So again, the x's are all changing by 1. They're going up, which is good. So then we're just looking how are we changing from one to the other. So this went down by 2. This went down by 4. This went down by 6. And then this went down by 8. Okay, so first of all, are they increasing or decreasing? Decreasing. The y values are decreasing, right? Now we've got to talk about the rate. Is the rate increasing or decreasing? In terms of the last one, right, it's reversed, right? It's picking up speed. It's decreasing more quickly. It's becoming more negative. So that's when they call the rate. So this is, again, it's going to go, if you were to graph this, it would look something like this, right? It's picking up speed as far as how quickly it's decreasing, but the rate is more negative, which makes it smaller. Okay, and that's always, again, it's a concept. When you get to calculus, you're always dealing with this. It's faster, but it's more negative, so we call that a decreasing rate. The rate is actually smaller because it's more negative. It doesn't make sense to me, but the thing is, can you think about it? So it's decreasing at a decreasing rate. Okay, because it's more negative. It's smaller. The rate itself is smaller. So that's what we're looking. This is a smaller rate. -8 is smaller than -2. And that's one of the things of math, that sometimes we get this sort of intuitive feel for things. But again, with me, a lot of times my intuitive feel is sometimes backwards. And again, we could do a quick, that's why I like having the key. It's decreasing at a decreasing rate. Okay, I know I always get those two wrong, because my intuition tells me oppositely. I'm looking at how fast. Okay, let's look at this last one. And who wants, we haven't, since they had 4, it's probably going to be increasing at a decreasing rate, or whichever one we haven't had. But we go from -18 to -10, that's actually an increase of 8, right? So I'll put a plus there. And then we go from -10 to -4 is an increase of 6. And then we go from -4 to 0 is an increase of 4. And we go from 0 to 2 is an increase of 2. So on the positive side, what's happening? We had an increasing rate of +8, and now we've got an increasing rate of +2. So it is actually increasing because it's going from negative to positive, so we can get rid of these guys. It's increasing, but the rate of increase is actually is less. And this one does work intuitively, because if you were to graph this, it does look like this. So the steepness slows down, the rate slows down. So on the positive side, our intuition tells us the right thing, or at least my intuition tells me the right thing. But when I'm on the negative side, it's backwards. Okay? We good with that? Makes sense? Okay. We're almost there. Let's clear that out. 38. Okay. And again, these are this will also help you like your first 1 or 2 weeks generally in calculus. We do this thing called limits. We don't really formally define it too much here, but it's just as we get close to a point, as we get close to an x value, what is happening to the y value. That's what a limit means. Okay, so we'll walk through this one. We're looking at this graph, use this information to evaluate each limit. So compute the limit as x goes to 5. When they have this little negative, I think of that saying coming from the negative direction or the left, right? So we're going towards 5 from the left. What's happening to the y value? As we get closer and closer to here, the y value should be 0. Right? Actually, we're looking for what would that value be, right? As we get very, very, very close to 5. Now, when it's all continuous like this, we could actually go to 5 and say, well, it's 0. So yeah, as we get closer and closer, as x gets closer and closer to 5, the y, or the limit, is going to get closer and closer to 0. Okay, that's all that concept is. Okay. Compute the limit of x as it gets to 5 from the other direction. Well, since it's continuous, the y value is going to the same place, kind of from a different direction, but it's also going towards 0, right? This line, if we follow this line and get really, really close to 5, we're going to get as close to 0 as we want. Does that all make sense? So for this one, it didn't matter if we came from the left or the right. Okay. Yes?
The answer key is different from 38. It says the A is infinity and the B is negative infinity.
Okay. Let's see what they've got here. Doesn't make any sense. Doesn't appear to be a hole there. That is 5, not -5. It is a continuous function. Since they don't show the graph on the answer key, I'm assuming they had a different graph, I'm not sure why it didn't get caught last semester. Maybe it did. Yes?
I think what it's saying is that for A, it's approaching 5 from the left side. So you look right to left and see it's going positive infinity, and then the bottom one is approaching 5 from the right side. So you look left to right, and it's going negative. So that's why it's negative infinity.
Well, when we get to this, I would agree with you, because this is going down to negative infinity. This is going up to negative infinity. But this is talking about the function as the function goes, as x gets towards 5, what is the function value going towards?
I know, but there's a homework question like that. I got it right here.
Yeah.
When's infinity to negative infinity, so I don't know.
Yeah. So I know what the answer is from calculus, and I'm not sure, I'll look into why they're doing that, but that's, unless this is like f of x is 1 over this, but if you give me this graph, the limit is simply, as I go close to x, what is the y value? Now, if there's a hole here, then we could, but even if there was a hole here, I'm getting close to 0. If there was an asymptote here, then I could go off to infinity or negative infinity, but that's what's happening at 5, both sides is going to 0. So, yeah.
So what you're saying is the answer key was answering something different?
It's either answering something different or it's wrong, because it's not talking about the limit concept. And I struggled with this myself, but it's 30 years of it. I know the limit concept is not, I don't see how they can get it to go to infinity unless the function, there's something missing here, which sometimes happens. If the function was 1 over f of x, then that would be the case, right? Because this is coming from positive, and then you're getting 1 over 0, which goes to infinity. And this, but this direction, from this direction, the y values are negative, so this would go to negative infinity if the function was 1 over f of x. So, and I've seen in the materials, because they're kind of developed here, so if this was 1 over f of x, yes, this is going towards infinity. And if this was 1 over f of x, this would go towards negative infinity. Okay. I'll research why they're saying what it is, because it's not what's there. And if this question, they don't have one specifically like this, but if it were on the test, I would take it off. Okay. So let's see if we do any better from here. X going to 0. So that's as x goes to 0 from the right. Again, the concept of limit is what is the function value going towards, and that should be 2.5. And I got 0.4, which if you take 1 over 2.5, you're maybe getting close. So that's what it's indicating to me, is that they're talking about the function being 1 over f of x, like here, see at the bottom. So I think, okay, I think they're all supposed to be like this, because if you do that, then I will come up with the same answers that they're providing. If all of these was the limit has to go 1 over f of x, because if you take 1 over 2.5, you get 0.4, so you'll match up their answer. Okay. And then, so let's just see if we approach these all as 1 over. So as x goes to positive infinity, so that's going out this way, f of x is going to negative infinity. So 1 over f of x would go to 0, because you've got a fraction with a really, really big denominator, negatively big, but the bigger the number of the denominator, the closer you are to 0. Okay. And then this one, same thing, even. See, this is really the same question, so I just, this, as it was written, goes to infinity. This goes to 1 over infinity, which goes to 0. And what do they have? Yeah, they've got 0, they've got negative infinity. So for D, I would say they've got the right answer, but I think what they've got here, these other ones should probably be 1 over f of x. So I'll contact the coordinator and see what's going on with this particular one. But that's the concept of limit, is as x gets close to a point, what is the y value going towards? Okay. Let's move on and forget we even talked about that. Okay. So now we've got two graphs, a g graph and an f graph. Consider those two. Let the function h be defined by f of x over g of x. What do you notice about the two functions? The two lines, they appear to be parallel. So if you take f divided by g, basically what that's doing is it's taking each y value, dividing it by the y value of the other, right? So determine the vertical intercept of h. Okay, so can we get a function for f? We've got a y-intercept, right? And we can figure out the slope, because if we rise 1 and we run 1, we get back on the graph, right? Rise 1, run 1, rise 1. So a slope of 1, does that make sense? Well, actually not 1. We rise 1, yeah. So we rise to 2, we run to 1. So yeah, it's you could do a half to a half, or so it's going to have a slope of 1. So the function for f of x is going to be x plus 1, the y-intercept. Y equals mx plus b. Does that make sense? Right? And then the function for g is going to be the same, except it's got a y-intercept of 3. And again, its slope, we go from 3 to 4, and then 4 to 1. So it's a rise of 1, a run of 1, a slope of 1, so 1x, or just x, with a y-intercept of 3. So we could write this, we know that h of x is going to be the x plus 1 over x plus 3. And I think for the types of questions they're going to ask, that might be the easiest one to do. So determine the vertical intercept of h. Vertical intercept occurs. What is the x value for a vertical intercept? For right here, what is our x value? X equals 0. So we plug in 0 for x's. So 0 plus 1, 0 plus 3 equals 1/3. So what is our vertical intercept for h? It's 0, 1/3. Okay, so if we were going to graph it, it would be, it's 1/2. We'd have a point maybe about there. And you can see it's f is in the top, g is in the bottom, 1 divided by 3. That works. Determine the roots of h. Roots of h. What are roots? That's going to be where it crosses the x-axis. Okay, so that's what a root is. And so that means when does the function become equal to 0? So we have x plus 1 over x plus 3 equals 0. And I did this earlier with the rational function. If a rational function is going to be equal to 0, which part is going to become 0, the top or the bottom? What happens if the bottom becomes 0 in a rational function? What does that give us? Infinity or undefined. So that doesn't give us 0. We need a 0 in the top and something in the bottom. That 0 divided by 1 is 0. Okay, so that's just telling you when you have a rational function, all you really have to do is look at the top, x plus 1. Right? When is x plus 1 equal to 0? Again, you could multiply both sides by x plus 3 and it cancels out, but really all we have to do is solve this x0 equals x plus 1, subtract 1 from both sides, we get -1 equals x. Okay, so that's going to be our root right here. -1, 0. That's going to be the root. And that's the only one, because it's still going to be a straight line. Straight line divided by a straight line is still going to give us, well, I think somewhat straight. Determine the vertical asymptote of H. So what causes a vertical asymptote? Vertical asymptote, because it's shooting off to infinity, is when we get division by 0. What would cause division by 0? The bottom to become 0, right? So we just look at x plus 3 equals 0, subtract 3 from both sides, x equals -3. So at -3, x equals -3, we've got a vertical asymptote for this function, which is not going to be a straight line, right? It's going to be a rational function. And so far we've got a point here and a point here, so we can kind of see it's going to go down like that. Determine the horizontal asymptote of H. How do we determine the horizontal asymptote for rational functions? Horizontal asymptote is when x gets really, really big in either direction, either -infinity or positive infinity. Okay, so if x is like 1 billion and you add 1 to it, does that make much of a change? No. If it's -1 billion and you add 1, no. So these numbers don't matter much. So the question to this for the horizontal asymptote, we just look at the two terms that are the largest or have the largest degree, x to the first, x to the first. And what is x over x? X divided by x is going to be 1. Doesn't matter what x is, right? 1 million divided by 1 million is still 1. So what this tells us is we have a horizontal asymptote at y equals 1. And so we're going to put that one in here. And again, there's a couple problems like this where actually they give a couple different examples, and then they ask you to sketch the graph. I can't remember which number it is, but there's another one that we do a lot like this. This one, basically what it added is that you have to come up with the rational function from what they give you. Is the value of the denominator of H ever twice as large as the value of the numerator of H? If so, when? So what does that mean? Is the denominator of H ever twice as large as the value of the numerator of H? So that would mean, is x plus 1 over x plus 3, does it ever equal the value of the denominator is twice as big as the numerator? Is it ever equal to 1/2? So is there some x value where the y value would be 1/2? Probably. And I could see it right here, because remember here this is 1/3. And again, because we have our asymptotes here, we could actually do a sketch of what this is going to look like. You could actually go ahead and graph that too, because we got it, right? And you'd see all of these things. And we can see, yeah, there's going to be a place where the y value is 1/2. It crosses that someplace. You could actually go ahead and solve this and see, you could find where it is, but this is just, well, I guess they say where, so, but I could definitely say yes. If we graphed it, what we'd do is we'd see, what's the value there, but to solve it, multiply both sides by x plus 3 and 2. So multiply both sides by 2. So you get 2 x plus 1. Multiply this side by x plus 3, right? And so what we're going to solve is 2x plus 2 equals x plus 3. and then we can solve for x. So I'm going to subtract x from both sides. So that gives us x plus 2 equals 3. Subtract x, you get that. And then subtract 2 from both sides. You get that x equals 1. And that makes sense. So it would be about right here where it would be equal to a half. So I've got it maybe going up too fast. Yes, it happens when x equals 1. Okay. At what x value is h of x equal to 3/5? So again, we would do the same thing. Set it equal to 3/5. But the key to all of this is coming up with that equation at the beginning. And again, we could cross multiply on these and then solve for x. So I'll leave that for you to do. And then they define k of x is g of x minus f of x. Create a sketch of the graph. So if we subtract the two, that's different than a rational function. And I'll just give you a quick, let's get rid of that. So subtracting these point by point, so g is always 2 above x because they're parallel, right? So what we're going to find out is it'll be this k function, g is on top, is going to be this parallel line that's right between the two as you subtract the two. And again, you could plot a few points and you would see that point by point, g minus f is halfway between. 3 minus 1 is 2. 4 minus 2 is 3, so there's a point there. You could go ahead and see that. Okay. So let me get one more question, 40, and then we'll have all the review questions covered. And still have about almost half an hour for either working individually or additional questions. Okay, so we're given a function, f of x equals x squared plus 3x. Determine an expression for the difference quotient of f over any interval of length h and explain its meaning. Okay, so difference quotient is something that actually comes from section 3.7. And there is a question on that. Does anyone remember what the difference quotient is? So it's really just the slope formula, right? So what's the slope formula? y2 minus y1 over x2 minus x1. But we're going to use function notation. So with function notation, we could think of it as f of x2 minus f of x1, so those are the y values, over x2 minus x1. But the difference quotient, what they're talking about is the 2 points we're going to use. We'll use one point, we'll just call it x and y, and then we'll use another point, we'll call it, well, maybe not y. We use function notation here. X and f of x. And so the second point is going to be what they're saying here, for any interval of length h, and explain. So it's whatever x is, we add h to it. And h could be a big number or a small number, but what that allows us to do is we can change h, and so we start with 2 points, and as we get h closer to 0, we get to having 1 point. And again, this is a concept you're going to pick up in calculus in probably the first 2 to 3 weeks. It's the idea of limits. The limit as h gets closer, as it becomes close to 0, what's happening to the 2 points? Well, the 2 points are getting so close to each other that they become 1 point. What it allows us to do is get the slope at a point, which is a major a thing we can get. So if we x plus h, f of x plus h. Okay. So the difference quotient, And here's f of x right here. And this one's going to be a little complicated, so what I'm going to do is I'm going to get my get a Word document. And I know one of the lessons, if you go back to 3.7, I've done this a couple different times. Our function is x squared plus 3x. So I'm going to go ahead and walk through this. Okay. And what we want to do is the difference quotient is going to be f of x plus h, so that's the y value of that point, minus f of x, all over x plus h, that's the x value of the first point, minus the x value of the second point. And notice what happens in the denominator. What is x minus x? 3 minus 3, 0. So whatever x is going to become 0. So typically what you see is the difference quotient is just the numerator. And in the denominator, they only show the h part. But when you do that, it doesn't look like the slope anymore, does it? It doesn't look like two y coordinates and two x coordinates, which it actually is, but the x's cancel out. Okay, so here's f of x. What would be f of x plus h? Everywhere there's an x, what are we going to put? X plus h. Okay, so this is the function that goes over here, and this is going to be the function that goes in the front. Okay, but notice we're going to have a little bit of work here. What do we have to do to x plus h squared? It's not x squared plus h squared, because we have to FOIL it out. We're going to get a middle term. Okay, so we get x squared xh hx, which we can also write as xh, and then h times h squared. The 3 we can distribute through. H, and then we can simplify a little bit. So I'm going to do that down here. So the first part is going to be x squared. Xh plus xh is going to give us 2xh plus h squared plus 3x plus 3h. So that's this first part. That's f of x plus h. From that, we're going to subtract f of x, x squared plus 3x. And I do it this way because what I see people, they'll just put the minus and they'll put the function. You need to distribute that negative sign to both terms. And that's typically what gets forgotten. I myself will forget it if I don't put those parentheses. Okay. And then what's in the denominator? H. So what I want you to see is there's a lot involved in this, but if you kind of see the whole process, it's not so bad. So we're just getting x plus h, plug it in as a composition. It's messy, but watch what's going to happen. When we distribute this, we're going to get a negative x squared and a negative 3x, right? So I distribute this negative sign. I've got a positive x squared here, so what happens when I have a positive x squared and a negative x squared? They become 0. What about a negative 3x and a positive 3x? That's 0. Notice the only thing that's left are things with h in it. Okay, so first step, we get rid of a lot of the messy stuff. We're left with 2xh plus h squared plus 3h, all divided by h. And then we can factor out an h, or just we can kind of go through and say, I like to think of this as just the distributive property of division, right? We're dividing everything by h, so we're going to divide out this h. When we divide this, there's 2 h's, right? H times h, so we're going to divide out one of them, and we're going to divide out this h. So we distributed the h from the denominator to all these parts. Okay. If you wanted to, you could rewrite it as 2xh over h. This is what I did, h squared over h, and 3h over h. And then you could say, okay, h divided by h is 1, h divided by h is 1, and this just becomes h to the 1. So our final answer is going to be 2x plus h plus 3. Okay. And you do this in calculus, and what you do is the last step is, now let's make h go to 0, which we can. Over when we had this fraction, we can't let h go to 0, right? Because you're dividing by 0. But if we let h be 0 right now, what do we get? 2x plus 3. And that's what we call the derivative. You just learned first 3 weeks of calculus in this one step, in this one problem. You'll see it again, so when you get to it, but I want you to know that the calculus isn't the hard part. The hard part was all the algebra that gets us there. The calculus actually becomes very easy. So that's what our goal is in this course. But for this one, that's all they wanted. When they talk about the difference quotient, this is what we would end up getting. We're not going to talk about the limit of h going to 0 yet. We save that for calculus. I think they had one other part to this question, so let's take a look at that. Let's just see that. I think that's, oops, not that one, this one. Yeah, so that's what they wanted. And then the last question, determine the value of the difference quotient for this function near the point 4 f of 4 when the length of h is 0.3. Okay. So x is 4, h is 0.3. So we take everything we've done, and we know that x is going to be equal to 4, h is equal to 0.3. It's not 0 yet. So we just take our difference quotient. We don't have to go rework it all again, because we would get the same thing for any particular point. We can just plug these values in. This is our difference quotient. So difference means we were subtracting the y's. Quotient means we were dividing, so it was really just a slope. So for the b part, all we've got to do is take this equation. We plug in the 4 for x. We plug in 0.3 for h, and the 3 stays 3. And this should give us, what, 4 times 2 is 8. 0.3 times 3 is 3.3. So that should be 11.3. So that's basically the slope when x is 4 for this function, and we go 0.3 away from it. So what this is saying is, here's 4, there's 4.3. The slope's going to be 11 between the 2 points on that graph, whatever, you know. So if we were to connect those 2 points. Does that make some sort of sense? Okay, it's a little bit more involved, and again, in the test, what the difference quotient does do is something like this, and they'll just ask for this final thing. again, if you can at least follow it, remember you're going to have 5 answers for this. You just got to pick the right one. And there'll be at least 2 or 3 of them that are just like wacko. And you say, no, those can't even be it. So now I got it down to 2. And they're going to be they'll be the 2 that are very close to each other, right? It always is. And so then you've got to, they might have one H plus 3, one H minus 3. But sometimes that's the hardest part, is knowing what the right answer is, but choosing it correctly. Okay? So my challenge to you is to do as much of the review test as you can. And again, working for understanding as much as you can understand. It's okay to watch the videos first, the solution videos, see how I go through it. It's okay to watch them at a faster speed. That's what I've gotten pretty good at listening at twice the speed. So all my professors sound like chipmunks. And I'm in a graduate, actually, hopefully will be my last semester, but I'm in a graduate program myself. So I know what it's, time is, you got to get through. But you can think much faster than I can talk. And I've been told I talk kind of slow. I'm from the West Coast, and people from Oregon, we talk a little bit slower. So at least that's what I've been told. So you could speed my voice up and maybe get me to normal speed or twice the speed. You'll be able to think circles around me, was what I'm saying. And sometimes that helps keep you focused, because that's what I do. Is if I listen to normal speed, my mind starts wandering. If I listen at twice the speed, I have to focus, because I'll miss something if I don't. But if I do, I can catch it better. So I think the technology is actually going to help us. And sometimes it's 1.5. It just depends on different people. Sometimes 1.75. Some of my professors, my own voice, I can do it twice the speed, because I do speak slower. Do that. Watch those videos again and again. The types of problems you're going to have will be slightly different, different numbers and stuff, but all the same concepts. And especially understanding those concepts of when they're asking about function notation, they want something like f of x times 5 or something, okay? So you'll see how they're going to go. Remember, when you get the questions, you're going to have all the answers. So sometimes you'll just be able to read the question and have a good intuition on which 2 are kind of the closest, or maybe the 3. You'll be able to get some out of there as long as you go through it. But if you can go through all 40, you have a better chance. And remember, everyone has equal chance now, because we can, no matter what you did on the first test, you can always replace that with 100% by doing well in the final. But don't worry about the first test now. Although anyone who didn't pick them up, I brought them all just in case if you needed them. But focus on this test, do well on this test, and then, okay, now I'll go back, study 1, and on the final I'll do good on that part, and I'll get that replaced with 100%. A pluses is still possible. B's, A's, they're all possible for everyone. And we'll work with you, and even through to the next test. So then we've got one more test before the final, and we'll get through that material. And that'll all be trigonometry stuff. So that's the rest of the course. We switch from algebra to trig. Some are you going to be happy, some are you going to be sad, and it just happens. I've got students who just struggle with algebra, but when they get to trig, it's like they're fish in the water now. They just swim off and they're happy. I've got people who've been doing good in algebra, and trig just doesn't make much sense to them. I do have an activity for extra credit that I will post, and I will highlight the first day after the test. It's a little PDF that you cut up, and you take these triangles, you move them around, and you actually just follow a video that I've made. And students tell me it really helps them make the connection of what's going on in trig. So it's something separate, but hopefully that's the one thing with trig, is if you can catch on to a few concepts, then it's something that can be learned actually fairly quickly. But you have to memorize a few things, but then it's like you can become an expert in a short period of time. It's also something, is if you don't catch on to those things, that it just doesn't make any sense for a while. But I think with that activity, it will help to make those connections. And that's what we'll do. Once we make those connections, trig will be straightforward. Just one more thing. When I was at Oregon State, I had a student was struggling in my algebra class. He asked if he could drop and take my trig class. I said, well, you need algebra to take trig? He goes, no, I looked at it, and he was from Mongolia, so a lot was language issues for him. He says, I can memorize my way through trig. He looked at the book, and I says, okay. And he says, all I need is one math class, and I'm done. And I said, okay, I'll give you a try. I said, I don't think it'll work, but prove me wrong. He had like note cards this thick for trig. He made his own. He got an A in trig. He couldn't get through algebra, but he got through trig with an A because he memorized his way. Okay, so trig is that way. It works differently. So if you're struggling because you've been good at algebra and you hit trig now, the good thing is that you kind of have to use a different process. The same thing's going to happen when you get calculus. Calculus is not harder than algebra. It's actually easier, but you have to approach it differently. So that's where this transition is going to be helpful for you. You'll learn to kind of learn a different topic in a different way, and that will help you when you get to your calculus. Okay, so I think that's all I got for you this morning. Any questions for the good of the order? All good? Okay, so I'm here for whatever you need, but you're welcome to take off, but do work through the practice test as much as possible. Don't worry about the homework. It's really unimportant at this point. The 40 questions in the review are what's important. When you come back after the test and go through some of that homework, it'll be easier. But focus on the review.